Hello guys, this is 7.4 relative rates of growth. Before we get into the topic, I would just like to give you guys an introduction or an overview of what we're going to look at in this section. Right, so let's consider the equation y equals e to the x. Right, a basic exponential function that we're pretty familiar with. And let's just give it a rough sketch. So let's say this line is y equals e to the x. Okay, now I'm gonna mark 1 here. So we know that y equals e to the x is an increasing equation, right? It keeps going up, and then we know that y goes to infinity as x approaches infinity. Okay. So we know that this function or this equation is growing pretty fast, right? It's increasing pretty fast, right? But as you know, that when we say fast, of course, we want to understand it by comparing to other functions, so we can have a better idea of how fast is it increasing, comparing with, for example, x squared. Right? We know e to the x grows much faster than x squared. Right? So this is the main idea that we're going to talk about in this video, is that how do we determine which function grows faster or slower? All right, so here we have a picture from the textbook, so that we can see that here we have three functions: x squared, 2 to the x, and e to the x. And you can see that all these three functions, they are all going up, right? As x increases, our y values are increasing as well. So just by comparing these three functions, we know that all these three lines will approach positive infinity as x approaches positive infinity. But if you look at these three closely, which line is growing faster, right? So you can see that e to the x is shooting up really fast, right? Even though these two are going up as well, but it's not as fast as e to the x, right? So in this case, I like to use another example, right? It's like you're riding a bicycle, right? As you pedal faster, you go faster. But is it as fast as a car, right? Maybe this red line represents the speed of the car, and x is the number of seconds that you pedal, or you put your foot on the gas, right? And e to the x may be something like an airplane, or like a fighter plane, right? So even though they are all going up, but also we know e to the x is going up much faster than these two. But how do we determine which one goes up faster, right? That's the interesting question we're going to look at. So this is the definition we're going to be applying. We have two functions, f of x and g of x, be positive for x sufficiently large. So as x approaches a fairly large number, we're assuming that these two functions, f of x and g of x, are both positive. Okay, so let's look at the first one. If f grows faster than g as x approaches infinity, then the limit of f over g as x approaches infinity will be infinity. Now let's just take a look at the first part. All right, suppose we have these two functions, f of x is equal to e to the x, and g of x is equal to x squared. Now we know that they are both increasing, and we know that e to the x grows faster than x squared. So by our definition from earlier, if we put them in limit form as x approaches infinity, f of x over g of x, we have limit x approaches infinity of e to the x over x squared. Now if you just go ahead and evaluate the limit, you get infinity over infinity, right? Which from 4.5 L'Hopital's rule, we know that this is an indeterminate form, so we would have to apply L'Hopital's rule. Right? So let's apply L'Hopital's rule, and then we have this. Right? So take the derivative of the numerator and denominator separately. We have e to the x over 2x. Now again, when you evaluate this, you still get infinity over infinity, which is still an indeterminate form. And by L'Hopital's rule, we can apply this again. Right? So limit as x approaches infinity, e to the x over 2. Okay, so by L'Hopital's rule again, we take the derivative of the numerator and denominator, we get e to the x over 2. And when you take the limit as x approaches infinity, what does the limit go to? That's right, it goes to infinity. Right? So by the first definition, we can say that f of x grows faster than g of x. Okay, so that's the idea. Now here, I want you guys to think about another question. So we're comparing an exponential function with a polynomial, right? So what if f of x is e to the x and g of x is any n degree polynomial? Which one grows faster? Okay, so I'm not going to answer this question in this video. Instead, I'll put up a discussion, and I want you guys to type out what do you think, which one grows faster, and why do you think that? Right? And the basic idea that we're using is by this short example that we have over here. All right, so let's move on with the rest of the definition. Right now, if equivalent, if g of x over f of x is equal to 0, that means g grows slower than f as x approaches infinity. Right, so depending on how you put the function, you can show that which function is growing faster than the other or slower than the other. Now, the second part of the definition, if both functions grow at the same rate as x approaches infinity, we will get this, right? When you take the limit of a quotient of two functions as x approaches infinity, we get some constant L. Now, notice that here we say that L is finite and positive, so that's very important. If you get the limit is approaching some number that is finite and positive, then we say that these two functions, f and g, they grow at the same rate. Okay, now we're going to look at some examples together. Example 1, we have two functions, 3 to the x and 2 to the x. Now, if you guys want to give this a try, feel free to pause the video. All right, so let's do this. As x approaches infinity, I'm going to put g of x on top, and then 3 to the x, f of x on the bottom, and let's see what we have. Okay, so of course, if you just evaluate x at infinity, you get infinity over infinity, which is not that informative, but there is some property that you can use from exponential function, that is the power rule. So what I'm going to do is I'm going to rewrite this as 2/3 to the power of x. Now, 2/3, that's a number that's less than 1, right? Now, when you take a number between 0 and 1 to the power of infinity, what do you get? That's right, you get 0. Now, from our definition earlier, we know that if we take the quotient of two functions and we get 0, it means that the function in the numerator, in this case 2 to the x, is slower. Slower than f of x, which is 3 to the x in this case. Now, if you want to try, you can put 3 to the x on top and 2 to the x on the bottom, and that will give us 3/2 here. And when you take 3/2 to the power of infinity, you get infinite, right? And that will give you the same result. Now, it doesn't matter which one you put first. You can say this, right? G of x is slower than f of x, or you can say that f of x is faster. I should say grows faster than g of x. Okay. Now, all in all, it doesn't matter how you do it as long as your result is the same. All right, next example 2. We're looking at two log functions, right? One with base a, one with base b. And here we're assuming that both a and b are greater than 1. Now, notice that we have not given a specific value to a or b. That's because it's not going to matter. And this is a pretty interesting example and pretty fun result that we're going to show, right? So let's compare f and g, right? Log a of x and log base b of x. All right, now, of course, again, if you just evaluate infinity, you get infinity over infinity. But in this case, we actually don't want to use L'Hopital's rule. We want to use the change of base formula. Right? Hopefully, you guys remember change of base. Right? And we are going to rewrite them as the same base with base e, or natural log. Right? So ln of x over ln of a all over ln of x over ln of b. Now, what we're going to have is very nice. We see that the ln of x, they reduce each other, leaving us just the limit of ln b over ln of a. Now, what is ln b and ln of a? Remember that b and a, or a and b, they are just some constant that we assign as the base to f and g, and they are greater than 1. That means what we're looking at here, the quotient of ln b and ln a, that's actually a constant, right? That means we can just drop the limit, and the limit is equal to ln b over ln a. So that is a constant. That is, I want to be a little more specific, that is a positive constant. And from our definition earlier, we know that if it's positive, it means f and g grow at the same rate. Grow at the same rate. Okay. Now, of course, this is from definition, but something that we can get out of this is, let's go back to the beginning of the question, right? We have f and g, they are two log functions with different base. That means even though we have different bases, they still grow at the same rate, right? So that's something I wanted to point out. And next, let's look at something a little more complicated. All right, here we have two functions. F of x is square root of x squared plus 5, and g of x is 2 radical of x minus 1 quantity squared. And we want to show that these two functions grow at the same time, grow at the same rate. Now, if you just go ahead and put them as by definition, right? Square root of x plus 5 over 2 rad x minus 1 quantity square. And of course, you can do that, and then you evaluate it, you get infinity over infinity, and then you have to take L'Hopital's rule. Now, I'm going to stop here. Imagine taking L'Hopital's rule of this limit, right? It's going to be very messy, right? In fact, it's not going to simplify your work by that much. So there is a different way that we can show that these two functions grow at the same rate. So the idea that we're going to use is that we want to introduce a new function, let's say h of x, and then we want to show that both f and g, they grow at the same rate as h of x. Okay. Show f and g grow at the same rate as h of x. Okay, and we're going to do that. Let h be the function x, right? And let's compare it with f first, which is the square root of x squared plus 5. Now, I'm going to show you like a little trick of how to pick h. Right, so you look at f is the square root of a polynomial. Right, now the degree of the polynomial is based on the highest term, which in this case is the x squared. Right, so we know that the term with highest degree is going to outgrow the others, right? Comparing x squared and 5, we know that as x approaches infinity, x squared is going to outgrow 5, right? So when we're looking at x approaches infinity, we can basically drop the 5, right? And then when you drop the 5, we just get the square root of x squared, which is x. Now x is just a monomial, and that will be pretty easy to work with. All right, so let's look at the limit of f of x over h of x. 5 over x. And of course, from this point on, feel free to use a L'Hopital's rule if you want to, but I'm going to show you a different way using algebra to kind of play around with this quotient to get it nice and easy. All right, I'm going to combine them into one big radical over x squared, and then split the fraction in here. All right, so I have 1 plus 5 over x squared. Right? And then we take the limit here. This term is going to go to 0, right, leaving us just a 1, which is a constant, right? So here we have shown that f grows at the same rate as h. Okay. Now, next we just need to show that g also grows at the same rate as h, and then we can say that f and g grow at the same rate. All right, so here we go. Which is infinity to radical x minus 1 squared over x. Right? And again, the L'Hopital's rule also applies here, but you can always play with algebra, right, to get what you wanted. Right, so in this case, I rewrote x as the square root of x squared. And then we have this nice thing, and we can do the same thing, right? Split up the fraction. And then we get 2 minus 1 over radical x, everything squared. And again, as x approaches infinity, our 1 over square root of x is going to go to 0, leaving us just 2 squared, which is 4. Okay? Now, You might notice this is a 4, and earlier we have a 1 when we compare f with h. Now it doesn't matter, as long as they are constant, they are a positive constant, we can say that they grow at the same rate. Okay, so this 4 tells us that G grows at the same rate as h. Therefore, we can conclude f and g also grow at the same rate. Right? So the idea of introducing an extra function that's a little easier to work with also, it's going to be very helpful in some cases, right? When your functions are very hard to work with, it's very hard to take L'Hopital's rule, and this is when you can think about, is there an easier function that I can introduce as a remediator between these two functions? All right, here we're going to introduce some notation, and I'm going to show you how to use these two notations later. So first one, a function f is of smaller order than g as x approaches infinity if the limit of f over g as x approaches infinity is 0. So in this case, if you look at what we have here for the limit, we can see that this is 0. That means the function in the numerator is growing slower than the function in the denominator. So in this case, f is slower than g. Then we can indicate this by writing x is little o of g, right? So x is smaller or slower than g. So the definition, second definition, let f and g be positive, and when we have large x, then f is of at most the order of g as x approaches infinity if there is a positive integer m for which f over g is less than or equal to m for x large. We indicate this by writing f is equal to big O of g. All right, so what we're seeing here, let me recap and go back to the first definition again. So the first definition gives us a notation to tell which function is growing faster or which function is growing slower. So in this case, f is growing slower than g and g is growing faster than f. We use f is little o of g. Now in this case, we use big O if these two functions, f and g, are growing at the same rate. Then we can say that f is big O of g. Right? So here is the key part. F is of at most the order of g as x approaches infinity. Now this idea is, or this notation is primarily, you will see this when you're, if you're a computer science major or when you have to do something with programming, mostly in engineering classes, and you have to construct algorithms and determine which one works faster, right? And which one works, or which one works slower, or maybe they work at the same rate. And this is when you will see these little o and big O notation. Now let me give you a few examples on how to use these two notations. All right, for instance, let's look at these two functions, x plus sine of x and x. So if you just perform the definition, right, x plus sine x over x, right? We know that sine, the range of sine is from -1 to 1, so this just oscillate between -1 and 1. And the x's here, they are most likely to be the dominant term. So we know that this is going to approach 1, right? So when we have constant, it means it's going to be growing at the same rate, right? So in this case, we can say that x plus sine of x grows at the same rate as x, right? But what we're going to worry about with a little detail, right, is that sine x can be 1, right? Sine of x is 1, or it can be -1, right? So the numerator is going to oscillate a little bit. So we say that x plus sine x is big O of x as x approaches infinity, right? Because they are growing at the same rate, and x plus sine x is at most or has the same degree as x, and that's when we use the big O notation, right? And furthermore, by definition, we can actually bound x plus sine x over x when we have large x by some constant, right? Now, we cannot pick one. That's not going to work, because even if we have just a slightly positive value, the numerator is going to be greater than the denominator, right? So what's a number we can pick here so that this inequality is always true, right? Now, we know that, the biggest value sine of x can produce is 1, right? So why not just make this a 2, and this will work, right? X plus sine x over x is always less than or equal to 2. Right, but this is by definition. Basically, when you can show that they, if two functions are growing at the same rate, by definition, we can say that one of them is big O of the other. All right, next let's look at ln of x versus x. Right, again, by definition, ln of x over x. Right, so well, by evaluating, you're still going to get infinity over infinity. So let's apply L'Hopital's rule. Right, and let's see what we get. Limit as x approaches infinity, 1 over x and 1. So that's just limit of 1 over x, right, which is equal to 0. Right, so we get 0. That means the numerator is lower than the denominator. Right, so we can say that ln of x is slower than x. Right, now with little o big O notation, we say that ln of x is of little o of x. Okay, ln of x is little o of x. Ln of x is slower than x. Right, that's how you use the big O and little o notation. All right, so let's do a quick recap. All right, so we started by introducing definition on how to compare two functions, where you use the definition, take the limit of the two functions in quotient form, and see what the result is. We have also show a few different techniques and introduce the big O and little o notation. All right, so that's it for today, and hopefully I'll see you guys during office hour. Have a good day.